Okay, now let me leave the practical domain and go to more theoretical issues that follow from this. What I want you to notice is the following. For a Carnot engine, Q1 over Q2 turned out to be T1 over T2, right? I did that for you here. Therefore, I'm going to write it as follows. Q1 over T1 minus Q2 over T2 equal to 0. That's just a simple rewrite. But I'm going to write this in another notation. My cycle had 4 parts. Remember, I did this, then I did this, then I did this, then I did that. In this segment, I had Q1 over T1. In this segment, there was no Q1 or Q2, or there was no Q because this is the adiabatic process. In this segment, I had minus Q2 over T2, and the last segment I had 0, and the whole thing is 0. In other words, what I'm telling you is the following. At every stage, if you looked at the heat absorbed by the system in stage I divided by the temperature of stage I, and you added all of them, you get 0. My process had 4 stages. Stage 1 is here, stage 2 is adiabatic, stage 3 is this, and stage 4 is 0 again. In this summation, Qi is defined to be delta Qi is the heat input in stage I, in the cycle or in the process. So we define Q2 to be positive even though it was rejected by the engine. But in this summation, the agreement I make is delta Q is positive if heat comes into the system, delta Q is negative if heat leaves the system. So why is that important? Now, this is the heart of the whole entropy concept. Remember, I told you there is nothing called the heat in a system. You cannot look at a gas and say that's the amount of heat in the system. Why? Because if you take a point there and say there is some amount of heat in the system, if you go through some kind of cycle and come back to the same point, then since you come back to the same point, internal energy doesn't change. This is the work done. Therefore, the work done is equal to the heat, and it's not 0. So in this example, what would have happened is you would have added heat Q to the system. So if there is some notion of how much heat is there in the beginning, you got that plus the Q that you added. And yet you're back to where you are. Therefore, you cannot define something and say that's the amount of Q in the system, because you are able to add Q to the system and bring it back to where it is. What happened, of course, is you added Q and you did some work. But the point is, you cannot say the Q here is so and so, but you can say the energy here is so and so, because if you come back to the same point, P times V is equal to 3 is equal to RT, and the internal energy of a gas is proportional to T. So the energy returns the old value. But now I'm going to tell you, so listen very carefully. Energy is a state variable because it comes to the starting value if you come to the starting point. It doesn't matter where you wander off in the PV diagram. Heat is not a state variable. There's nothing called the heat at that point because I'm able to go on a loop, change the value of Q or add some Q to it, and I come to the same point. So there's no unique Q associated with that point. But there is a new unique quantity S called entropy, which has a fixed value at a given point. And if you go for a little loop in the PV diagram and you come to the same point, S will return to the starting value. So who is this S? That S is defined by saying that the change in the entropy is the heat you add divided by the temperature. In a tiny little process, if you are at some temperature T, you add a little amount of Q, keep track of all the changes, and that change will be 0, as I showed you in this Carnot cycle. You can show more generally that if you take any path, not just the Carnot engine, bounded by adiabatic and isothermals, but any path you take, you can show that the delta Q added up is not 0, but delta Q over T, namely give a weighting factor 1 over T to the heat you add, then the positives and negatives cancel and give you exactly 0. In other words, Q1 was not Q2. Q1 was bigger than Q2. But Q1 over T1 precisely balances Q2 over T2. The heat absorbed at higher temperature, if divided by T1 to compute the change in entropy, then in the upper part of the Carnot cycle here and the lower part of the Carnot cycle here, the two canceled as far as the entropy change is concerned. So the entropy is a new variable. It's a mathematically discovered variable. What we find is that if I postulate there's a variable called entropy, the change in which in any process is the heat transfer divided by temperature, then that has the property that when you go around on a loop, you come back to net zero change. That means every point can be associated with a number you can call entropy. Entropy is like a height. Suppose you're walking around on some landscape. Each point is a height. You can walk here and there and come back. At every stage, you keep track of the change in height. If you come back to where you are, the change in height will add up to 0. That's what I told you in the case of a potential energy function. It is just like a potential energy function. The internal energy and the entropy are now state variables. At every point, the gas has a certain internal energy and an entropy. They deserve to be called state variables because when you go on a loop and come back, they return to the starting values. Now, you have no idea what this quantity stands for. You agree it's bizarre. Work done, we understand. Heat absorbed and heat rejected, we understand. What is delta Q over T? Why is dividing by T make such a big difference? Why does it produce a new variable? We can see it is true. At least in the Carnot cycle, you can verify in detail that the change in the total of all the delta Q's over T is in fact 0. So we'll develop a feeling for what it means, but historically this is what happened. People realized, hey, that's another state variable. We introduce a new variable. We have no idea what it means, but it is a state variable, so we better take it very seriously. So I'm going to tell you what it means. But first, I want you to get some practice calculating the entropy change for a couple of processes. So let us take, for example, 1 gram of water, or let's say m grams of some substance. It's got some specific heat, C. And I change the temperature, say, from some T initial to some T final. I do that by keeping the system, starting the system at Ti, and I should never be far from equilibrium. That's one of the conditions on this. In fact, you can say it should be always near equilibrium. So the system starts at temperature T initial. I put it on a heat bath, which is infinitesimally warmer than this. Then I let it heat up to that point. Then I put it on another reservoir, slightly hotter than this one. At all stages, I want the system to be almost near equilibrium. In the sense of calculus, you can make the difference as small as you like, provided you do enough number of times. And slowly, I raise this guy from here to here. At every stage, the system has a well-defined temperature. There's a well-defined heat input, and I want to add it all up. So what's the change in entropy? S final minus S initial is equal to dq over T, summed over all the parts, or I should write it as an integral, as mc delta T over T. Do you see that? dq is mc delta T. But I got to divide by T, and that integral is done between some initial and final temperature, and we can do this integral rather trivially. It is mc log T final over T initial. That is the increase in entropy of some m grams of some substance of specific heat C that's heated from T initial to T final. We're just getting practice calculating this. We still don't know what this guy means, so don't worry about that right now. If you did not divide by T, what are you calculating? mc delta T integrated is just mc times change in temperature. That's the old calorimetric problem you did. How many calories does it take to raise the substance from some initial to final temperature? That you understand. When you divide by T, it's a thing you don't understand, but anyway, Let's make sure we know how to calculate the increase in entropy when water or something is heated from a lower to a higher temperature. If you cooled it from a higher to lower temperature, you can use the same formula, Tf over Ti, but Tf will now be smaller than Ti if you cooled it. So log of a number less than 1 is negative, and the entropy change will be negative. So let me do one more entropy calculation. That's going to be pretty important for us. That entropy calculation is this. Take a gas and watch it expand isothermally from some starting point at some fixed temperature T. It goes from V1 to V2. What is the change in entropy when it goes from here to here? Again, the system must always be in equilibrium or near equilibrium, so I can plot it as a point in the PV diagram. So I slowly take grain after grain, do the whole thing I told you, and find S2 minus S1. This is 2, and this is 1. That is equal to sum of all the heat transfers divided by temperature at every little step of the way. But remember, this is also the same as P delta V over T. Why? Because on an isothermal, du is 0. I've repeated it many times, but you got to know this. Delta Q is P delta V. But P over T is N RT over V delta V. You also want to divide it by a T. You understand? P over T is NR over V. So P is equal to nRT over V. I'm just saying PV is nRT. So P over T is nR over V. Now dV over V, when you sum or integrate, will give you nR log V2 over V1. That is the change in entropy of this gas when it went from volume V1 to volume V2 at a given temperature.